All right, welcome back. So, basically, this week we're just going to finish off our acids and base unit. So, we're going to be looking at kind of modifying our Arrhenius theory to include some discrepancies that actually happen with observable chemicals. We are going to look at the strengths of acids and bases, and we're also going to be looking at something called polyprotic substances. So acids and bases that can react more than once or have more acid or base characteristics. So first, just a little reminder on the Arrhenius theory. So, and this was kind of right at the beginning of our acids and bases. We had acids ionize in water to produce hydrogen ions. This was the original theory. So our ionization equation was we start with our acid, we produce our hydrogen ion and anion. So for example, we had something like HCl, which is a strong acid. It ionizes to produce H plus and Cl minus. And that is why all acids needed to have a hydrogen present. Now for our bases, we had bases dissociate in water to produce hydroxide ions. Now, because it's dissociate, remember all bases were considered ionic, so we have our base produces our cation and hydroxide. So for example, our sodium hydroxide can dissociate to produce our sodium ion and our hydroxide ion. Notice how we knew if anything had hydroxide, it would be considered a base. Now, this theory does have some limitations, and that is not everything is going to have hydrogen on the left, or the combination of COOH is going to be an acid, and not everything, not all bases have hydroxide. Now, normally we would do a lab where we would test a bunch of different things and actually see this. But these are actually just two of the main points that you would actually have from this lab, and that is solutions like ammonia, NH3, or sodium carbonate show basic properties. So if you notice, ammonia or sodium carbonate does not contain hydroxide. So that is one reason there why we needed to modify our thing. Is like there's a lot of compounds out there that can have acidic or basic properties that don't contain hydrogen and don't contain hydroxide. Now another thing that we would have noticed is carbon dioxide and aluminum nitrate show acidic properties when in solution. The same thing, there is no hydrogen present. So something funny is going on here. Now, also, if there's stuff like metallic oxides, like calcium oxide, or even non-metallic oxides, like nitrogen oxide, they can act sometimes as acids or bases, once again, depending on what's there. And even substances can act as both acids or bases. So, for example, NaHCO3, so sodium hydrogen carbonate, which is basically baking soda, it can actually act as an acid, and it can also act as a base, depending on what it's paired out with. Now, if it's paired out with water, it'll be basic, but if it's paired out with hydrochloric acid, it'll neutralize it, so then it acts as a base. Or if we pair out with sodium hydroxide, it acts as an acid, because it neutralizes sodium hydroxide, so it's a funny little thing. So, because of that, we need to modify our Arrhenius theory. Now, our modified Arrhenius theory, this is going to involve the reaction. Major keyword difference here, because before it was either an ionization or dissociation. Our modified Arrhenius theory involves a reaction of dissolved substances with water. So an acid, an Arrhenius acid now, our new definition is going to react with water to produce hydronium in aqueous solution. So our new generalization is our acid plus water produces H3O plus and an anion. So this should be H3O plus here. That's not really that clear. Now, if you're given ionic compounds, hydrogen-containing polyatomics like HSO4, so hydrogen sulfate, hydrogen phosphate, dihydrogen phosphate, etc., it should be HPO small 4 minus, not 4 minus up top. That was a little typo there, so please go back and fix that. We need to make sure to dissociate the ionic compound first before showing the reaction with water. So for example, if you do have something like NaHSO4, because this is ionic, it's going to dissociate first into Na plus and then H SO4 minus, and now this can now react with H2O. So basically, if you do have a polyatomic that's hidden within an ionic compound, dissociate it first so it turns into a two-step thing, which we're going to get into when we get into using our modified Arrhenius theory to predict reactions, or justify reactions, not really predict. So now, for hydrochloric acid, instead of having it ionize, what we're going to do, by our new definition of Arrhenius acid, now it reacts with water. So this is the first time we should be seeing something plus H2O, because we have never written it like this before. So now, during this reaction, the hydrogen is going to transfer over to our water to form our hydrated water, or a hydronium, and then plus our anion Cl minus. So that's that example. Now for example 2, we have our sodium hydrogen sulfate, hydrogen containing polyatomic. So in this one right here, this is going to be a two-step reaction. And all of the ones that contain a hydrogen and a polyatomic will be like this. So step 1 is dissociation. Because remember, ionic compounds won't react with water, they're just going to dissociate, right? So that's why we need to do it this way first. And these here molecular compounds are able to react with water because they don't dissociate, right? So technically the ionization is just the reaction. So for sodium hydrogen sulfate, NaHSO4, it's going to dissociate first into our sodium ion, then plus our hydrogen sulfate. And now, step 2, now we have our reaction with water. So in this case right here, if you look at the example up here, we had hydrochloric acid. There was this transfer of this hydrogen. So if you want to think of, which one is going to be acidic, either sodium or hydrogen phosphate, obviously the thing with the hydrogen here, that's how we kind of get our hydronium. So it's the hydrogen sulfate that will react with water to produce our hydronium and our sulfate ion. Now please pay very close attention to the charges as they're going through. And then of course even the chemical formulas as well. So you can tell the acids where basically we are transferring this hydrogen here, so this is how we get our hydronium. But we know that we're forming an acidic solution because of this right here. As soon as you see hydronium present, you know you're forming an acidic solution, because that is not going to change. An acid is still hydronium. Now, as for our bases, same thing, an Arrhenius base, it can dissociate or react with water to produce hydroxide. Now, as I said with the one up above, when ionic compounds come in contact with water, they dissociate. So if you do have an ionic compound, the first step is going to dissociate. Then if you don't get hydronium or hydroxide produced off the dissociation, then you can start looking for a reaction. And we are going to produce hydroxide because anything with hydroxide is considered a base, right? So for example, if you're given an ionic compound, make sure to dissociate the ionic compound first before showing the reaction with water. Or if you're just given a molecular compound, it's a one-step reaction with water. So for example, ammonia is NH3. If we wanted to show how this can act as a base, it will need to react with water to produce. Now, our hydroxide is going to show up. Now, notice hydroxide is basically water missing that one hydrogen. So basically one hydrogen is going from water to the ammonia, which ammonia had an original formula of NH3. Now it's going to go NH 4, because it has that extra hydrogen, it's positively charged. And that is just making sure where everything is no charge over here, so negative plus positive is neutral over here. So that is how molecular compounds will happen. Now, if we are given same thing, in this case right here, it's a ionic compound for sodium carbonate, step 1. Dissociate ionic compound. And if we don't see hydroxide, then it's going to react with water. So in this case right here, sodium carbonate is Na2CO3. It's going to dissociate into 2 sodium ions and our carbonate ion. Now we'll notice that we do not see hydroxide here. So step 2. We're going to get a reaction with water to produce our hydroxide. Now in this case right here, if you're thinking about, if we look at everything that's happening and how even up here we had that transfer of the hydrogen, and then of course our water became positively charged because that hydrogen ion is positively charged. So that just means that basically water is positively charged. Or sorry, not water, the hydrogen that we're transferring is positively charged. So if you're looking at what could potentially react with water that's going to attract a positive hydrogen, it's this negative charge on the carbonate, right? So negative ions attract our H+. So what that means, it's our carbonate needs to react with our water to produce. Now we are going to get hydroxide, OH-. Now where did that hydrogen go? Well, now it's onto carbonate. And it produces hydrogen carbonate. Now, if you have trouble with these charges, just knowing that the hydrogen carbonate is going to go on, or the hydrogen goes on carbonate, but if you are having trouble with just charges, just remember in your on your table of polyatomic ions, all of those are here. So for example, the carbonate, right, is right here, CO3 2-, but the hydrogen carbonate is just down below it, HCO3- is right here. So there is a way where you can actually see them. So this is a little clearer, right? Hydrogen carbonate HCO3-, so you can see the charge here. And it's all going to be in your periodic table, so just make sure to double check the charge on the ions in your periodic table as well. Right, so our next page. Now note, because if you have a metal hydroxide like lithium hydroxide, there's no need to show a reaction with water because hydroxide ions are already present in the original step. So for example, like I said, for all ionic compounds, you dissociate first. So if you dissociate lithium hydroxide, you produce the lithium ion plus hydroxide is already present. So you're not going to get a reaction with water if hydroxide's already there. All right. Now, basically, our last thing right here, I'm sorry, I think this is the last one. We're just going to show the modified Arrhenius theory. Let's go back here. All right, so we're going to show the modified Arrhenius theory to show the reactions with all these here and showing how they can act as either acids or bases. So obviously the ones that have like perchloric acid, nitrous acid, sulfuric acid, obviously all these here are acting as acids. So make sure to show the reaction with water. And the carbonate ion, barium hydroxide, and sodium cyanide, well, obviously this one here is going to be a base, but the carbonate ion acting as a base, sodium cyanide acting as a base. All right. So just remember you're showing the reactions with water. So perchloric acid is HClO4. So show the reaction with water. Now it's an acid, so remember it needs to form H3O+. So that means the hydrogen is going to leave here and go on to our water. So we get H3O+, and then we write our perchlorate ion, ClO4-. All right, so see if you can try get the other one. So I'm gonna the answers are going to go up in about 3 seconds. So if you want to work on these on your own, just pause the video and work on them, and then you'll see the answers in a few seconds. All right, so looking at some of the answers, this is kind of how everything is going to play out. So nitrous acid and sulfuric acid look like this. Now you will notice for these here, I'm only showing the transfer of one hydrogen because I'm only creating, oh, this should be H3O plus, sorry. So I'm only showing the formation of one hydronium or one hydroxide. So that's all we're really going to worry about for these here. Same thing with our carbonate ion, transfer of the one hydrogen over, it's acting as a base, we get HCO3 minus and OH. Barium hydroxide, we only showed a dissociation equation because it's already an ionic compound. And for our sodium cyanide, this is one where it's an ionic compound, right? So dissociation equation first to produce our negative ion, then our negative ion will react with our water to produce our hydroxide. That is how we do those. We're using the modified Arrhenius theory to prove that sodium cyanide, barium hydroxide, carbonate ion will act as a base. Now, of course, in your notebooks, there's going to be a few more examples, so just make sure to go through these here and just get comfortable with the difference between the modified Arrhenius theory and the normal Arrhenius theory. Now, last thing, just for this one here, there is limitations with the modified Arrhenius theory as well because it cannot predict reactions, it can only explain them. So this is one of the big things, just so you know, that it can't predict, it can only explain. So you need to know the results in order to use it. So for example, the sodium hydrogen phosphate, just by looking at that formula, it can either be acidic, basic, or neutral. The only way to tell is to actually test it, but just to kind of show you on how it can act either neutral, acidic, or basic. For example, if it's neutral, hydrogen phosphate is HPO4, 2 minus, so it's Na2HPO4. If it's neutral, for this sample, it's just going to dissociate. So you'll notice in this example right here, there's no hydronium or no hydroxide. So if you place this in water and all it does is just dissociate, well, now it is a neutral substance. But we will notice it does have a hydrogen ion and it is negatively charged. So based on two of these characteristics, we don't know if it's going to lose this hydrogen or it's going to attract a hydrogen. And that's it. We just don't know. So this is why there's a huge limitation with this modified Arrhenius theory. Now, once again, if we knew the results, we can prove, well, if this, for example, does act acidic, then we'll know HPO4 2 minus can react with water to produce hydronium. In this case right here, it's going to be PO4 2 minus, or it can act basic and produce this. Now the thing is, we don't know. Like I said, just by giving sodium hydrogen phosphate, there are 3 possibilities that could happen, and there's no way to predict it. So the only way to tell for sure is you need to do a diagnostic test like litmus or use indicators. So that's why, for example, when you look back on the ones you just done, it'll either have acid in its name, or the question will tell you to prove that it's acting acidic or prove that it's acting basic. You're not going to be able to predict if it's going to be acidic, basic, or neutral. Now, last little thing to go on with this here, so just kind of acids and base, or this little particular thing, is something called neutralization reactions. So we looked at how substances can act as bases, or substances can act as acids, what happens if we put something in water, but we haven't looked at what happens if we actually combine an acid and a base together. So when we do, we get a neutralization reaction. Now, this is just a special type of double replacement, which you've seen before, that happens between an acid and a base. So it produces an ionic compound, which we call a salt, and it produces water. Hence, that's why it gets its name, neutralization. So our generalization, acid plus base, produces salt plus water. So for example, nitric acid, HNO3 plus sodium hydroxide. So this is technically just a double replacement reaction because we're replacing our sodium and our hydrogen. We get this combination of HOH, which is basically just H2O. So that's why we get H2O, that's our water, and we get our salt of sodium nitrate. And that is how they happen. Now, you will notice that everything in here is basically aqueous except for the water. So we will look at something called net ionic equations as well. Now, what these are, we're going to dive more deeply into them when we get into our stoichiometry unit. But a net ionic equation is a chemical reaction that only includes the reacting entities and omits anything that does not change, and we call these spectator ions. So a spectator ion is present, but it does not take part in a chemical reaction. So how we figure out what is going to be actually taking part in a reaction or not, what we're going to do is break in our reactions into 3 steps. We're going to look at balanced reactions, then we're going to look at total ionic, so basically we're going to ionize or dissociate, and then we're going to look at the net. So let's look at our example again. So nitric acid plus sodium hydroxide, it produces water plus our salt. Now, we'll notice here all these here have aqueous, aqueous, liquid, and aqueous. So for the total ionic, all we do is either we ionize or dissociate anything that should be there. Like we know nitric acid is a strong acid, so technically it doesn't exist as HNO3. It exists as H plus and NO3 minus. Same thing with our sodium hydroxide. This is a soluble ionic compound. It's going to dissociate into sodium ions plus hydroxide ions. Water is a molecular compound. It doesn't do anything. Now for our sodium nitrate, it is also aqueous, so it is going to dissociate into its ions. Now by writing it the equation like this, we'll notice that nitrate ion, so NO3 minus, is on a reactant and nitrate ion is on the product side. So it's the exact same ion, exact same charge, nothing has changed with it from reactant product. So technically, it didn't do anything for this reaction, right? It didn't change. And the sodium ion's the same way. On our reactant side, it's sodium positive. On our product side, it's sodium positive. So it too done nothing. But we can see hydrogen and hydroxide combined to make our water. So we call this the net reaction, because these are the only reacting species. The anions and the cations don't really do anything. And all reactions or neutralization reactions will occur like this. So for example, I want you guys to try this one on your own. So hydrobromic acid reacts with calcium hydroxide. So the answer is going to go up in a few seconds, so just pause the video and see if you can get this one. Alright, and hopefully you got something like this. So our balanced reaction, we got 2HBr plus CaOH2 produces our 2 waters and calcium bromide. Now if you check the solubilities, strong acid, ionized 100%, soluble ionic compound, going to dissociate. Same thing, calcium bromide, soluble ionic compound is going to dissociate. So our total ionic, when we dissociate everything that can be dissociated and ionized, is going to look like this. And then of course we'll notice that our bromine ion didn't do anything. It stayed the same. Our calcium ion also stayed the same, and the only reaction occurred look like this. Now because they all have the same coefficient, we drop it and we just get our neutralization reaction that looks like this. So all we can say, neutralization reaction is defined as a reaction between hydroxide and hydrogen to produce water. So we can summarize all neutralization reactions like so. Or remember, we can substitute hydronium for our hydrogen and get this. So that is it for this lesson. So our next 2 is just going to look at some acids and base strength and of course polyprotic species. These here will be much shorter videos. This one here was a little longer. So anyway, just make sure to practice stuff in your workbooks, and I'll see you guys for the next one.